Hello dear students, welcome to video number 13 on the topic chemical kinetics, the channel pen and paper chemistry. We are going to cover the subheading molecularity in this particular video. So before we get started, please make sure that you have pen and notebook ready to take down notes for offline reference. Let's study a few reactions first. We have the reaction N2O5 breaking down to give us N2O4 plus oxygen. Now in this particular reaction, only one molecule is involved. So one molecule means we can call it as a unimolecular reaction. Second reaction, 2HI, that means two hydrogen iodide molecules colliding. Collision is taking place to give us hydrogen and iodine. So two molecules involved in this collision or reaction, hence a bimolecular reaction. For those who've been watching the videos regularly, we've already covered collision theory in a separate video. In case you are not familiar, please watch that video first. 2NO plus O2 giving us 2NO2. Now here three molecules are colliding to form a product, so it's a termolecular reaction. Three molecules colliding. See, it is easier to visualize two molecules colliding with each other in order to form a product. But if you have three molecules colliding to form a product, it becomes a little difficult. So more the number of molecules, more is the difficulty in collision, right? But nevertheless, these molecules are colliding with each other in order to form the product. Now, based on what you can see here, I have given the names unimolecular, bimolecular, termolecular, and so on, right? So what do you understand by the term molecularity so far? We can say the number of molecules, atoms or ions that collide with one another at the same time to result in a chemical reaction or to result in the formation of the product. But what do you think would be the molecularity of the reaction which has popped up on your screen now? You see over here we've got 2KMnO4 plus 5SO2 plus 2H2O. Of course, this is a balanced chemical equation. But does that mean 2 plus 5, 7, 7 plus 2, 9? Does that mean that 9 molecules or atoms or ions are colliding with one another at the same time to give us the products? Does that mean that the molecularity of this reaction is 9? Can you imagine 9 molecules, no matter how small they are? Can you imagine 9 molecules? It's a little difficult to visualize, correct? So let's rethink about our concept of molecularity once again, right? Because what you are seeing may not exactly be the case. It is not necessary that entire 9 molecules are reacting in one go. Maybe this reaction is taking place in a number of smaller steps, and this may just be the final reaction. So before we go ahead with dealing with molecularity in detail, we have a few definitions over here. Complex reactions. Reactions taking place in a number of steps. Elementary reaction. Each step out of that complex series of steps becomes the elementary reaction. What will be the rate determining step? I've written the definition over here, although I will explain the concept also. Rate determining step is the slowest step in a series of complex reactions. So what do we mean by this rate determining step? So for example, let's suppose we are having a relay where one person goes and hands over the baton to the second one. It's running really fast. The second person goes and runs and hands over the baton to the third person. Now comes the third person. Our third person is little slow. It's going very slowly, right? Oh my God, we are running late, so we need to pick up, and so the fourth person also runs fast in order to complete the relay. In this entire process, who defines the rate at which the relay was done? Yes, it's the slowest person in this race who, of course, the others are covering up, but what is there is this is a chain, right? So one following the other. It's the space of the slowest person which is going to define the outcome of the race, correct? So same way, when you have a reaction, for example, I'm taking here a reaction wherein N2O5 changes to NO2 and O2. This is one of the examples that we are taking wherein the final reaction comes out as N2O5 changing to NO2 plus O2, and we can balance this reaction. So we have 2N2O5 giving us 4NO2 plus O2, right? Now what has been observed here in this particular set of reactions is experimentally we have seen that the rate of this reaction is directly proportional to the concentration of N2O5, dinitrogen pentaoxide, and also during the course of reaction we found intermediates NO2 and NO3 being formed. So how do we explain the formation of the products in this reaction, considering that our final reaction is showing participation of 2N2O5 giving us 4NO2 and O2, but there is no NO3 in our products, right? That means NO3 is some intermediate which is being formed. So we have this mechanism given in order to explain the formation of the products for this particular reaction. So what do we have over here is N2O5. Our first step of the reaction involves the slow breakdown of dinitrogen pentaoxide to NO2 and NO3. Now, have you ever heard of NO3 molecule? We definitely have an ion, but not a molecule, right? So it's very unstable. We don't find it existing normally. So this NO3 goes and collides with another N2O5 molecule. And because NO3 is restless, it can't survive, it can't be alone. So it wants to change. So this reaction becomes very fast compared to the previous step, which is slow, resulting in the formation of 3NO2 and O2. In order to get the final reaction, what are we going to do? We are going to add up the two steps of this reaction, and we get over here 2N2O5. Our NO3 and NO3 will get cancelled, and we will have 3 plus 1, 4NO2 plus O2. That's the final reaction, right? In other words, this reaction, which otherwise appears very simple, which appears, as if just two molecules are colliding to give us the products, is not as simple as it looks. It's actually a complex reaction made up of the elementary steps, right? These are the two elementary steps. And which will be the rate determining step? Obviously, the first one, because that is a slow step involving the generation of NO3, which will be used up in step 2. Unless NO3 is generated, it cannot be used up, right? So the rate of the second reaction is actually dependent on the rate of the first reaction, which in turn is a slow step. So let's go back to our definition again. Rate determining step, the slowest step in a series of complex reactions. What do we mean by mechanism of a reaction? It's a series of steps or elementary processes which are proposed. Okay, we don't see them actually happening, but based on our observations, based on what we detect in the reaction mixture, we propose in order to explain the overall reaction. Right? Have you written this down? Okay, now, as I said earlier, in this particular reaction, we have observed experimentally that the rate is directly proportional to the concentration of N2O5 at any point of time. So, what does it tell you about the order of this reaction? What will be the order of this reaction? Yes, absolutely, it is 1. It is a first order reaction. Again, order of reaction has been separately explained in the set of videos, and we have also derived expressions for first order and zero order reactions. The integrated, graphical, everything has been covered on the channel. What about the molecularity? So now, I cannot define molecularity simply as the number of molecules which are participating in the reaction. It's a complex reaction, right? So that means my complex reaction has been broken down into a number of steps. So look at the steps. This is our rate determining step, correct? Now in the rate determining step, how many molecules are involved? Only 1. So the molecularity of this reaction technically is actually 1, which we determine by observing the reaction mechanism. So you understand the difference between order and molecularity. Perchance the order and molecularity of this reaction is the same, but it need not necessarily be the same every time. Now, when molecularity is 1, we call it as a unimolecular reaction, right? Whereas order of reaction will give us the rate equation. So rate is equals to the rate constant into the concentration of N2O5 raised to the power of 1, right? Here I have another example for you. Based on your understanding, you have to answer the questions that follow. It says the mechanism of a reaction is found to follow the following steps. So that means this is the mechanism of the reaction, and we have listed the elementary steps. So step 1, step 2. I have got step 1 involving NO2 plus NO2, slow reaction, conversion to NO and NO3. Step 2 is NO3 plus carbon monoxide, which is a fast reaction getting converted into carbon dioxide and NO2. Now both reactions are balanced, right? What do you have to see? Based on the above, answer the following questions. So first question is, what will be the equation of the final reaction? Look at the two equations carefully. I have not given you the final equation. What will be the final equation of this reaction? Of course, our NO and NO3 are intermediates which are being formed over here, right? Second question asks you to find out the molecularity of the reaction. So which reaction or which elementary step will give you the molecularity of this reaction? Third question is, can you determine the order of this reaction based on the information provided? If yes, then what is the order? If no, why? Now, please pause the video. I'll give you the answer in the video itself, but for your, to boost up your learning and to boost up your morale that you are understanding, try answering these questions. Some of you may have already answered, I'm sure. Okay? Okay, let's go ahead. Now, the first part of the question says the equation of the final reaction. Or should we do the third part? Now, look at the information which has been provided to you. We've just been given the mechanism of the reaction. The question says, can you determine the order of this reaction based on the information provided? No, we cannot, because there is no mention of experimental data as to how the concentration of NO2 is affecting the rate of this reaction, right? Remember, order of a reaction is an experimental quantity. You cannot determine it by simply looking at the equation. So the answer to this question would be no, because there is no experimental data indicating the change in the concentration of NO2 with change in time. Again, okay, let's go on with the reverse order only. Molecularity of the reaction. Of course, molecularity will be determined by the slow step, and how many molecules are participating in this slow step. Of course, there are two molecules which are colliding, so the molecularity of this reaction would be 2, and it's a bimolecular reaction. You have to give the equation of the final reaction. Now, in order to do that, let's write down the two equations once again and find out which one is intermediate and which will be the product. So, I've got these two equations listed over here. Both the equations are equally balanced. Now, you notice over here, NO3 being generated in the first step is being used up in the second step by an equal amount. So, done away with. NO2, you have two molecules being used up, but at the same time, one NO2 molecule is regenerated in the second step. So, what does that mean? One NO2 and one NO2 gets cancelled. So, what are we left with as the final equation of the reaction? So, we have NO2 plus CO gives you NO plus CO2. Basically, nitrogen dioxide oxidizing carbon monoxide to form nitric oxide and carbon dioxide. Right? By the way, this would be a second order reaction based on experimental data, not otherwise. We cannot determine that only by looking at the equations. How many of you got all three right? Let me know if you got all three right by posting 3 smileys in the comment section of this video. So we need to redefine molecularity. Although in some places you will find the previous definition, let us be more precise in our definition. We say molecularity can be defined as the number of molecules, atoms or ions. Oh, look at that. I have not input atoms or ions involved in the rate determining step of a chemical reaction, right? Okay, you can very clearly see I am ready to tabulate the differences between order and molecularity of a reaction. So first things first, can you give me the definition of order of a reaction? So that will be my first point. The sum of the powers to which concentration terms are raised in order to express the rate of a chemical reaction. And molecularity we have just now defined above, right? What about the second point of difference? How do you determine order of a reaction? Yes, it can only be determined experimentally, right? Molecularity depends. If it's a simple reaction, then from the reaction equation itself. But if it's a complex reaction, then we see the mechanism and we define it by the slowest step. What will be the third point of difference? You remember we said that order of a reaction can be a fractional value, right? Maybe and maybe not. It could be fractional as well, right? Whereas molecularity, on the other hand, is always a whole number. You can never have half a molecule colliding, half an atom colliding, right? It's always a whole number. What about the fourth point of difference? Yes, order is for an overall reaction, whereas molecularity, no, we don't say molecularity of the whole reaction, right? Molecularity is based on the slowest step, right? So what I've done over here is I have jotted down the points elaborately for you all, except for the definitions. I would want you to write the definitions yourself, please. That will be a good revision as well for you. So 3 points, and then we go on to the fourth point. Order is for the overall reaction, whereas molecularity is based on the slowest step. So let's suppose I give you this equation. What is the order of this reaction? Yes, the order would be 2 plus half, because we've been given the rate equation. So 2 plus half gives us 2.5 or 2.5. What will be the molecularity, assuming that it's a simple reaction? Yes, of course, we will do 1 plus 1 giving us 2, because I just now said that assuming it's a simple reaction, meaning to say it is involving only one step, where carbon monoxide and chlorine molecule collide with each other and combine to give us carbonyl chloride or phosgene, right? Please practice a few questions on this topic so as to get a firmer understanding of this heading, right? In the next video, I shall be talking about pseudo first order reactions. So please stay connected, because that I think would be the last video in this topic. So see you in video number 14. Stay safe, stay healthy, stay happy.